What is up, everybody? Welcome to CS302 Online. Today, we're going to be learning one of the most important topics of the course. And by important, I mean like very hard. I would say it's the second hardest behind recurrent relations. And that is AVL trees. I even put a picture of Thanos because scary stuff that we will learn. And not to discourage you, but more to warn you that you have to be very careful about this topic because, frankly, like after doing it so many times, I find it kind of just trivial and easy. But historically, people that have taken the class, not just my section, but any section, have said that it's the hardest topic that they've had. If they didn't have recurrence relations in their class, they said AVL was the hardest. If not, they said recurrence was hardest, and then AVL. So, I don't know. I guess we'll find out together as to why that's the case. But before we can jump into AVL trees, I kind of want to pick up where I left from last class. So going back to last class, we were talking about binary search trees and what they are in comparison to just a binary tree. A binary search tree allows you to, as the name implies, to search to a tree to find some data in hopefully a faster fashion. But as we have it implemented right now, the time complexity is O of n, because while the binary search tree, like the advantage is that when you got a node, the number smaller than that node has to be on the left, so you can go search there, or if it's bigger, it has to be on the right. In the ideal case, if the tree is balanced or with the lowest possible height that it could have, think back to those first properties we talked about when we first talked about trees. And we were talking about the height and what the minimum height of a tree should be given a certain number of nodes. That's basically 2 to the power of, you gotta take the log function, because remember, each of these levels can fit 2 to a certain power, so like if you want to find out how much a tree with sort of 3 levels has, if you have like 1, 2, 3, it's just going to be basically 2 to the third power minus 1 because of the first level. So that would be 7 nodes, which makes sense because the first one has 1, then the second has 2, and then the third has 4. 1 plus 2 plus 4 is equal to 7, right? And the next level, which would have 8 nodes, would be 2 to the 4th power, which is 16, minus 1, 15, because 7 plus 8 is indeed 15. So that would be the minimum height that it has to be. And if we have such a tree where the height is indeed the logarithm, then we can say that the search time is also in logarithmic. So let me maybe put that in writing. So we know that based on those properties that we talked about on day 1 on trees, we know that the minimum height of a tree with with n nodes is 2 to the, the minimum height of a tree is 2 to the n minus, this is the number of nodes. For that, it would be the log, be the log of the number of nodes. Okay? And probably take the ceiling function of that, if I was to guess, because let's test it out. So log of 7 would be 2 to the 3.9 something, right? Because would be because 2 to the third power is already 8, so it's actually 2.9 something, right? So the ceiling of that would be 2 to the third, essentially, so 3. So that is indeed correct. The height would be 3. Of course, the whole height 0 being 1 node or no nodes or whatever, that be plus minus 1 depending on how you're measuring height of 0. But for me, I am saying that this would be considered height of tree. Okay, because I got 1, 2, 3 nodes there. Okay, so I'm counting basically the number of nodes. Similarly, if I said I have a tree with 10 nodes, let's say, I have a tree with 10 nodes, what is that going to be? That is going to be, again, in this case, to the 3.2 something power. Okay, because 2 to the 4th power would be 16, so somewhere between 3 and 4. So we take the ceiling function is going to essentially be 4, okay? So here's the thing about 4. No matter where, even if these 3 levels are full, we have to have one more level. Now, amongst this level, how many nodes do we need? Well, so far we got 7 nodes. We need 3 more. So they could be here, like that. You know, that would make it what is that? A complete tree, right? And but they don't technically have to be. They could also be here, you know, or this one could be here. It doesn't matter, because anywhere that they go, we cannot make it less than 4 height. We can make it more, like, you know, it could be something like this, and then now we have a height, you know, height of 5. I'm just saying, in the best case scenario, we can't make it anywhere less than 4. Okay? And here's the thing: if the height of the tree can be measured with logarithms, what we're saying is, think about it. What is the height here? It's the number of checks we have to do before we get to a leaf node, right? And the height is always the worst case, because, again, if one single node is like this, then we consider the height to be 5 in this case, right? So the height is very much like big O in terms of having the worst case scenario, which is, again, the one where you have to go through most nodes to get to that leaf node. And each of these nodes that you're checking is potentially a comparison you're making between 2 numbers, right? You're saying, for example, say you're looking for 20. You're looking at the 52, and you're checking whether 52 is greater than, less than, or equal to 20. So in this case, 52 is bigger, so that means that 20 has to go on the left side. So that's one check that you're doing, right? So in this case, in the worst case scenario where you're going pretty much the longest distance from the root, that means that you're doing 4 checks, right? So that means that the algorithm is having to do 4 comparisons, which in relation to the number of nodes that you could have potentially compared with is log n time, is log n comparisons. So that is why I'm claiming that the time complexity for you to be able to search through this tree where the height is as lowest as possible is logarithmic. And that, of course, is good. And by the way, something I wanted to clarify based on what somebody asked me, and maybe I never said these terms. When you see something like O of n squared, O of log n, this is also known as linear time. And that's because n is just, you know, like if you were to plot this, it would be in the form of y equals mx plus b, right? And so it's just a line. The steepness of the line doesn't matter, but it's just a line, right? That's why this in this case, this could be rewritten as opposed to c n plus b, which is kind of like saying where n is equal to the power of 0, right? Like that. Okay, so that's kind of what we're writing this as. But at the end of the day, it's just a straight line. So that's why we say this is linear time. This is quadratic time because it makes a parabola. So I believe that is called quadratic. Yeah, I think so. Yeah. And then this one is called logarithmic. Okay, so just wanted to make sure that we're on the same page. When I say linear, I'm talking about O of n time. Okay, so anyways, back to this. The problem with this assumption that we're making here is that we are assuming that the height of the tree is the least amount of possible. But on the complete other side of the coin, like we said with the example with the degenerate tree up here somewhere, well, we said it, I don't know, it's somewhere in here. But the example with the degenerate tree was when we gave it a list that was actually already sorted. So let's say we're inserting 1, 2, 3, 4. 1 goes there, but then the 2 is greater than the 2. Sorry, the 2 is greater than the 1, so it has to go on the right side. And then the 3, which is the next number we're inserting, is greater than 1, so it goes on the right, but we already have something there, so we check the 2. 3 is greater than 2, so it goes here. And so basically that's why this forms a degenerate tree. This, of course, the height is equal to the number of nodes, which means that you have to check all of the nodes basically to identify where whether you have the value that you're looking for or not in the worst case. So this is actually linear time, just like a linked list is, essentially. So if we want to achieve logarithmic time, which is better than linear time, we need to find a way to make sure that the tree has the lowest height possible, or in other words, the tree is balanced. Now, that's easier said than done, because here's the thing. Okay, I'm inserting a bunch of these. This is not really balanced. What will be a balanced representation of this? Well, something like this would be okay. That's close enough. I mean, there's you know there's no way to make this into two levels. You have to have that one extra level for that one more node, right? But there's other ways of doing this. Also, you know, it might not be so obvious when you're inserting things that they're balanced or not. Like for example, let's say that you build this tree that's balanced, okay? But now you want to insert a 5 in there. Well, the 5 has to go to the right of the 4. So now, again, it looks pretty degenerate to me. So then you're like, well, now I got to change everything around. So like you have to like rewrite the tree and maybe put a 3 in the middle. And then you're like, well, you know, the 2 is going to go there. So that way I can put the 1 here. Because if I put or I could also put the 1 here like that and put the 2 here. And on this side, I could put the 4 here and the 5 like that, or I could put the 5 here and the 4 like that. It doesn't really matter, but I have to basically move things around in the tree, and as I'm doing it now, I'm kind of eyeing it. What we are going to be doing with AVL trees is come up with a systematic, algorithmic way of doing what are called rotations, which is basically taking certain nodes in the tree, moving them into different spots in the tree to achieve a balanced tree. And of course, not only do we want to insert and balance it as we insert, but also have the ability to insert later on and maintain balance. Okay? So that is what brings us into AVL trees. So AVL trees, you know, the dark side of the forest is a pathway to many abilities. In this case, AVL trees is a pathway to a balanced tree. Okay? So, yes. So, what does AVL stand for actually? Well, AVL is actually the name of the people that came up with this, and their names are Georgi Adelson-Velsky, and the other person is Eugenio Landis. And they together in the year of 1962 came up with the AVL tree algorithm. Okay? So before I show you how it works, let's talk about what they consider to be a balanced tree and what is not balanced. Okay? So balanced trees. And I did talk about this very briefly when I first talked about trees, and I said I talk about it in detail now. Well, now is the time. Okay? So, let's do it. I did see somebody claim the extra credit, so make sure you send me a message on Discord so I know who you are. That way you can get your points on Canvas. Okay? Cool. So, let me go ahead and draw a tree here so that I can talk about it. So, let us first look at this tree right here, and let's put some numbers in, but it has to be a balanced tree. So if I put a 50 here, the numbers on the left side have to be less than 50. They could be anything. They could be negative numbers for all you care, but I'm gonna put a 20 in there, and maybe I'm gonna put a 10 here, and then the number here. Here's a question for you: what set of numbers could go there? What range of numbers could go there? So question mark. Go ahead, somebody tell me there what goes. And in the meantime, I'll show you other stuff. And then let's say we put a 60 here. Okay? So we are looking at this tree, and we're trying to find out whether this is a balanced tree or not. So here's what you're going to do. A balanced tree can only have a difference in height between the left and the right childs of there. So if we're looking at a certain subtree, oh, we got some responses. Ooh. So we got like 4 responses at the same time. There's probably a big delay because I asked that like 30 seconds ago. So the first person said the range was 20 to 50, and then somebody else said the range was 21 to 49, and then somebody said between 20 and 50. Well, I'm sorry to tell you guys, but I don't think any of you got it absolutely completely correct, because the way that I've been claiming to do my trees is that duplicates go on the left side, right? You can make them go on the right side, but technically speaking, I've been following the rule set of going on the left side. So I guess the closest person to get it would be maybe this person, the one who did this, because this one on top can't work because if you keep your duplicates on the left, like I said, then you couldn't have a 20 there. You could definitely have a 50, but not a 20. So that one wouldn't work. And if you keep your duplicates on the right, which is not what I'm doing, but could work too, then the 20 would be okay, but then the 50 would not. So, and then somebody said 2150 over here. That one is correct. The person that said 2150 is correct. Oh, that's a new one. Because you said 2050 first, I think. Yeah. But yes, 2150 would be the correct case here. Because it would go anywhere after 20, which would be 21. And it could include 50. So the correct range would be 21 to 50 inclusive. Okay? I suppose when you said between 20 and 50, no, that would be technically correct because the word between does not include them, but you have to include 50. So yeah. So yeah. So that's a good question. I like that. Okay, but anyways, so yes, you guys are all on the same page now. Good. So going back to this, the way that you calculate the height, you're going to look at the height of a certain subtree. So you're only looking, if you want to compute the height of a certain node for an AVL algorithm, first identify the node that you're going to work with. So let's say that we're working with this node. We would like to compute the height of that node. The way you compute the height of that node is you compute the height of the left and right subtrees. Now, the left and right subtrees, I say the word subtree because in this case it's just a single node, but there could be nodes beneath it, like there could be more other nodes. So I am just calling it subtree. The way you write that is just the word sub and then tree. Okay? So the way you do that is you're going to add 1 to the height of the previous node subtree. So whatever the node subtree is here, you just add 1 to that. Okay, well that doesn't really get you anywhere because you don't know what the subtree of that is. So the way you do this recursively is first, you go all the way to the leaf nodes and you work your way back from the leaf nodes to the root. So when you're at the leaf node, what is a leaf node, by the way? A leaf node is, again, one that does not have a left or right child, okay? In this case, the height of a leaf node is going to be a height of 0, okay? So both 10 and our mystery node, which I guess we'll just pick a number. Let's pick 50 for it. So in that case, this also will have a height of 0. And technically speaking, the 60 will also have a height of 0, okay? So now, as we go back in the recursion, as I said, the height of this node is basically the addition of the previous of the subtree from the left side or the right side plus 1. So in this case, we're going to take 0 plus 1 to get on the left side to be equal to 1, and on the right side is also equal to 1 because we take the 0 from here plus 1, which is 1. Okay? So now, if we want to compute the height of the 50, we're going to take the biggest of these two numbers and add plus 1 to that. In this case, they're both equal to 1, so we just take 1 plus 1. So the height of this on the left side is 2. Let's look at the right side now. For the right side, we need to compute this. Of course, we go to the recursion all the way to the leaf node and then work our way back up, which in this case is in 60. So we get 0 plus 1, which is 1. Okay, so what is the total height of this node? We pick the biggest number of the two, which is a 2. Let's do a bigger example with more numbers in it. Fixed. 54. Let me pick a bigger number so I have more range of numbers here. 60, 81, 91, 88, 0, 20, 22, and then 1, 2, 3. Okay, so let's compute the height of this tree. All right, so, or the height of each node, better yet. So what we're going to do is we want to compute the height of this. So to do that, we need to compute the height of this of the children. So we got to compute the height of this. But to do that, we need to compute the height of this. And to do that, we do that. So basically, we go all the way to the leaf node. So we and by the way, this is the way that I recommend you do this on a test. Keep tiny little numbers on each side representing the height of the subtrees. Okay. In this case, it's 0 for both because it's a leaf node. Okay. So if you want to compute the 2, what you do is notice that the 2 has no left child. So in this case, the height of that is going to be 0. In fact, it's going to be 0 for all of these on that side. On the other side, however, here it's going to be a 1 because 0 plus 1 is 1. Then you get 1 plus 1, so you get this is actually 2 here. And then this becomes 3 here. See how I'm adding 1 to that? I'm also taking the biggest number of the two, which just happens to be, of course, the number. Actually, that's not 0. So over here, it gets a little bit more interesting. 3 plus 1 is 4, so this becomes a 4. Here, it's 0, 0, so 0 plus 1 is 1. So here we got a 4 and a 1. So to compute the next one here, we take the biggest number. Obviously, the biggest number here is a 4. So we do 4 plus 1, and we get 5 on the left side. To compute the right side, we got to start from the leaf nodes. So let's start from this one. 0, 0. This becomes a 1 because 0 plus 1 is 1. We can't compute yet the right side here because we got to compute the other node. So recursion takes place. This is a 0 here. This is a 0 here. Actually, before we compute that 0, we technically go to the left. If you're doing this kind of like the standard way, kind of like you're doing in order traversal almost. So then you get to the 88 and you get a 0, 0. 0 plus 1 is 1. And then on the right side is a 0. Here you take the biggest number of the two, which is a 1. So you add 1 to that. So here now you get a 2. Of course, you take the 2 instead of the 0 here and add 1 to that, so you get a 3. So here we got a 1 and a 3. You take the biggest number always. So take the 3 and add 1 to that. So 3 plus 1 is 4. And that is going to be this. So the final height of this is going to be a 5. That's the one that you would pick, okay? Is that correct? Well, you see 6 nodes here technically, right? You see that we got essentially 1, 2, 3, 4, 5, 6. That's okay. With the AVL algorithm, you want to get a 5 there. It's how it just works, okay? All right. Next thing is, this is how you compute the height, but I still haven't talked about what is considered balanced or not. What is considered balanced or not is if the height between the left and right subtree, so if the height between the left and right subtree, if the difference, let me write the word difference actually. So if the difference between the height of the left and right subtree, if the difference between the height of the left and right subtree is greater than 1, make sure that 1 looks like a proper 1. They are not balanced. In other words, if the difference between the left and right subtrees, spell that, subtrees height is less than or equal to 1, the tree is considered balanced. So I'm basically writing the opposite I said here. So let me read this again out loud. If the difference between the height of the left and right subtree is greater than 1, they are not balanced. So what I'm claiming is that if the numbers I'm looking at here on each level, so like this number and this number, if that difference is more than 1, not balanced. By that logic, this is okay, it's considered balanced. This is also considered balanced. This is not considered balanced. Not balanced, not balanced. This is technically balanced up here, as is there. Not balanced, or sorry, balanced, 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 not balanced here, not balanced here. Okay, so maybe I should use different colors for the not balanced ones. So that's not, actually, technically speaking, green sounds better for balance. That's what we're trained to because of traffic systems in the world. So yes, that would be all the green ones are balanced and all the red ones are not balanced. Okay? It's interesting that this shows us balance because that will give us a thing about how we should be checking for balance. Because technically speaking, this tree by AVL standards is not balanced, because it's not just about the root node showing balance. Every single node in the tree has to be appearing as balanced for this to be considered a balanced tree. And in this case, I see a bunch of red nodes there. So they would all have to be green for this to be considered an AVL tree that is balanced. So we got some work to do to balance that tree up there. Maybe we'll come back to that example. Okay? And then I've reworded the other way around too, which is the difference between the left and right subtree. Height is less than or equal to 1. The tree is considered balanced. Okay? These are not technical definitions, but I'm sure you find pretty much the same thing in any book than this, as long as you understand that difference. Now, it's interesting that you make sure that you understand it says greater than 1. Okay? That means that a difference of 1 is still considered a balance. It's only a difference of 2 that's not considered balanced or bigger. Okay? That is why when I reword it here, I say is less than or equal to 1. Okay? Less than or equal to 1, that is considered balanced. It's only when it's 2 or more that is not balanced. Okay? Make sure you understand that part. The reason they allow that flexibility is because imagine that you have a tree that is like as full as it can be, but you have one more node. So you put it there. That's balanced. But technically speaking, this node has 1, 0 there, right? So it's impossible to make this like, if you wanted to always have all the nodes be exactly like equal, that this tree would be impossible to make, because like the algorithm would be like, what am I going to do with this node? Like there's no way for me to balance this. So because of that, it does allow that flexibility, which has some interesting side effects. That you will see some trees that don't necessarily look balanced to the untrained eye, but they are balanced in the force. Okay? So, yes. By the way, I love AVL trees. They're one of the fun topics. Like one of the funnest topics to do. They're cool. So, anyways, as you can see, that's balanced, 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 balanced. And then I didn't draw any of the zeros, but balance, 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 balance. Okay? So, this would be a happy AVL tree. Bob Ross will be proud of this tree. Okay? So, all right. So now we know what a balanced tree is, but we don't know how to achieve this power. So to achieve this power, we need to learn about rotations. So rather than me writing the rotations down, I'm just going to copy and paste the 4 main rotations that you should know. Be aware that even though it's 4 rotations and they all look different, you could technically achieve this power by just learning one of them and then understanding that the other ones are derived from any one of them. Okay? So, time for some copy pasting. I gotta be very careful that I don't break this copy pasting, which I already did. I'm gonna try it again. The reason I'm copy pasting is because I'd really rather not have to redraw these rotations. Copy. These are the ones that you definitely want to print out and have next to you when you're doing the test. Like, make it a poster in your wall. Admire it. There we go. Okay, so let's talk about these. By the way, I did not know the AVL guy's name by memory. I read it off of that. So there are other stuff, yes, but not that, because I'm very bad with names. So yeah. I don't want to claim that I just knew that guy's names, which I did not. I actually had to Google it last semester when I wrote it here. So, okay. Before I just flat out show you the table as you've seen there, let me kind of build up to it. Okay. So let's insert a tree that we know is degenerate. Okay. Let's do a 3, 2, 1 insertion. Okay. So for inserting into the tree, you follow the binary search tree rules, which is like small things on the left, bigger things on the right, equal things. We are committing to going with the left for those, okay? So I guess, yeah, we'll do 2 1s then so you can see that. So we start out by putting in the tree as the root node because it's the first thing that we are working with. So far, we check the height. Every time that we insert something into the AVL tree, we want to check the height of the tree. And technically speaking, this will maybe be more obvious as the example becomes bigger. You will see that if the subtrees beneath what you're inserting should never change in height because you're not modifying that. It's only going to be things above where you're inserting that could potentially be changed, not things beneath you. Okay? So like if you have this massive tree that's built up, you know, all over the place, and you're inserting something here, this height's not going to change at all. Only this stuff up here is the height's going to change because it's not connected to that. Okay? So again, that might not be obvious right now, but as you do this, you'll see why that's the case. All right, we got to insert a 2 now. So the 2 is smaller than the 3, so it's going to go on the left side. Cool. All right, we finish inserting. The next thing we do is we check to make sure that we follow our AVL property. So we are looking at the zeros here, and we can see that now this node has a 1 and a 0. Now that is still okay because, again, height difference can be 1 and still be okay. 0 or 1 are okay. By the way, when I say difference, I'm talking about you can take the absolute value of that. So, you know, when you're actually coding this, you know, don't get confused and try to do like 0 minus 1 and end up with -1 and you're like that's not okay or something. Just take the absolute value of the subtraction of them, okay? And that will fix any weird things that could happen. So, anyways, I'm just saying that because I've seen people have issues when they're coding AVL trees because of that. So, anyway. Going back to this, we're going to go ahead and insert the next number because we're still balanced. So we're going to insert the chosen one that will unbalance the tree. So 3, so 1 is smaller than 3, so it's got to go to the left of that. And it's smaller than 2, so it's got to go to the left of that. So, you know, he was supposed to bring balance to the force, not leave it in darkness. But in this case, the chosen one has leave this unbalanced because now this gets updated to 1. But this gets updated to 2. So now it's no longer in balance. Because this is okay, but that is not okay. All right? So, how do we fix it? Well, I can come up with one solution off the top of my head that would fix it for sure. But is there more than one solution in this case? Not really, actually. Yeah, there's no more. There's only one solution where this would fix it, and that would be to change what the root of our tree is. Instead of making the tree the root, we look at the tree and say, okay, we know that this tree is left heavy, right? If you're holding this with a string, you can see how it's kind of tilting this way because it's really heavy on one side, right? So like if you got a scale, you can see how it's really wanting to go this side instead of being balanced, right? So from a gravity point of view, where would we want to hold this so it's balanced? We'd want to grab it pretty much from the 2, right? Because that's right in the middle. Let's say we hold it from the 1. What's going to happen if we hold it from the 1? If we hold it from the 1, you know, we grab the 1 instead of the 3. Now it's going to like tilt all the other way around. And so yet again, it's going to be unbalanced in the other way. Because we're going to have 0, 0. 1, 0, 2, 0, right? So it's unbalanced. It totally shifted the balance to the other side, but achieved nothing in terms of balancing. So really, the only place that we can balance this from is by grabbing it in the middle. So taking the 2. So what we're going to do is we're literally going to pull it up like that. So let me redraw this. What we're going to do is we are going to take the 2 and we're going to make it the root like that. And that's going to make the 3 fall to the left side like that. And now we have restored balance to the tree while still maintaining the binary search property, right? Because here's the thing. You can just be like, oh, okay, this is unbalanced, then go ahead and do this. Now it looks balanced. Well, yes, technically speaking, this is balanced, but this has violated the binary search property of the numbers on the left being smaller and the numbers on the right being bigger because 1 is not bigger than 3. So we are still trying to achieve balance while maintaining binary search property. That's why this one only has one solution, which is this. There's no other way you could organize this while maintaining balance. Okay? There will be more cases where there can be different orders, but in this special case, because it's such a small tree, there's no other way. So this, what you see, is essentially a rotation. In fact, this is the most basic rotation that you need to know, and the only one that you need to know, because everything else kind of gets derived from this. The idea of taking this tree and rotating it by changing what the root node is, and things kind of rotating, falling into place. Notice that we didn't have to unplug anything from this tree. The connections were still the same, just kind of different ordering of them. All right, so we achieved balance. So now we're going to insert another one. So where's that other one going to go? The other one is going to go to the left of the current one, like that. Okay, are we still maintaining balance in the tree? Well, this is 0, 0, but this becomes 1, 0. This becomes a 2, 1. And as you can see, this does not change, because that's kind of building into what I was saying, that you're modifying a completely different part of the tree, so it's not going to change that. So we don't need to recompute that and waste time doing that. Check that out. It's still balanced. Even though it's a difference of 1, it's okay. It is still balanced. In fact, if I inserted a 4 here, then this will become 2, and it would still be balanced. And let's say that I inserted a 0. Okay, if I insert a 0, then it's not balanced. Because as I work my way up, 1, 0, 2, 0, right there, I break the balance. You don't even worry about updating this yet, because you got to fix that before you go further, okay? You want to solve the problem before it becomes bigger. So the moment you see something unbalanced, you fix it there. You don't keep going up. Well, how do we fix this tree? The same way we fixed the other one, actually. We just kind of take that middle node, and make it the subroot. So basically, rotate that. Whoa, the special effect kind of failed a little bit. But yes, do that. Okay. Yes, let me just fix that by rotating it. There we go. Okay. And then relinking that as such. Okay. Is this balanced now? Have we achieved balance? Restored peace, freedom, justice, and security to this empire. Well, this is a 1, 1. And this is a 2, 2. So yes, this is indeed a balanced tree now. Okay? You can see that that was the same rotation. It's just that in this case, we did it to a subtree instead of the entire tree. Notice that nothing changed on top of it except for recomputing the height. What if the 2 had 2 children in it? Okay, let's rewind. Wait, the 2 had 2, it does have 2 children in it. Oh, I see what you're saying. So you're getting a little bit ahead of me, but that's okay. So I think what you're saying is, let's say we had the following tree. 4, 2, 1, and then we had a 3 here. Is that what you're saying? Like if we run into some situation like that? Even, here's the thing about this. We should never run into this situation, because when we inserted either the 1 or the 3, then this would be unbalanced, and we would have fixed it. However, how we could run into it is, let us say that, how could we run into this? I don't know if we could ever run into a situation like that. I'm trying to think of one where we could. I think I have an idea for that. So let's say we have a 5 here, which would make this a 1. And then I don't know how we could run into that situation, but I can show you another situation we could run into. Let's say that in this tree we inserted a 0. Then this would be unbalanced as 1, 0, 2, 1, 3, 1. All right, there we go. So we kind of run into the situation, sort of, okay? So yeah, okay, so let me do that slower so you can kind of see it. Okay, so we currently have this tree. We're going to compute the heights of it. So we got 0, 0, 0, 0, 1, 1, 2, 1. Okay, and we're going to insert the number 0 into it. Or it could be another 1 too, it doesn't matter. All right, so we recompute the heights. So 0, 0, then this height becomes 1, 0, which is perfectly fine. But this one becomes 2, 1, which is still perfectly fine. then the root becomes 3, 1, so the root has a problem, okay? The root has a problem. So there is kind of like the situation that you were saying, because by our logic from before, we want to make this the new root, right? We want to jank it up. But now we have the situation that it already has a child in it. So what do we do then? Okay, not to fear. We can attempt to do the same sort of rotation and sort of work with it, okay? So let's try that. So what we got to do is we want to make the 2 the root, and these guys up here, we would want to ideally bring down. The problem with bringing them down is that we already have a child there. So what can we do? Well, this is where it gets a little bit more interesting. So what you do, and I have a visualization tool that I found online. I don't want to share it on the video because copyright probably, but I will link it on the description and I'm going to post it here. This is a great video because it shows you the rotations happening live. Okay. What rule did I break? I don't have any. Oh, you mean the one up here? Yeah, good point. Let's make this 1.5 and fix that. That takes care of that issue. Or just make it a 2. Didn't notice that earlier. Sorry. But anyways, going back to this example. So yeah. So this is where it gets a little bit more interesting. As you said correctly, there is a 3 already is there. So the 4 is going to kick the 3 out. It's going to kick it out of that spot so it can take over that spot. So essentially, what's going to happen is, and I really wish I could animate this better, but this is still going to flip down here like such, but it's going to kick out the 3 from that spot. So it's going to look like this. So the arrow is going to be up like that. And then the tree is going to be like, bam, kicked out. And then this is going to come down here. So then you might be asking yourself, but what about the poor tree? What are we going to do with it? It's not a happy tree right now. Not to worry. 4 is going to adopt it. And it's literally going to become his child. Like that. So 4 is like, move aside. I'm taking over here. But don't worry. I'll take care of you. You're not my child. So aggressive adoption, I would say. And yeah, that pretty much takes care of this, I think. Because here we got 0 zeros and we got a 1 0 on this one because it has no children. Here we got 1 1 and then we got 2 1 and we have solved the unbalance and brought balance again to the tree. Okay? So this whole item replacement is called it's still a single rotation, but it always happens to the same location. So it always happens, like you said, to that right child of what is going to be the new root node, if there is already right childs to the old root node. Okay? So when I show you these rotation that I copied and pasted from my notes, they already take that into account. Okay? Let's stop there before I show you those rotations. Now let's actually look at them. Yeah, let's look at them now. I think now it'll make more sense now that we see them. All right, so these go by left and right rotations. I'm left-handed, so maybe that's why I keep doing right rotations. They just seem more natural to me. But that's the one that I always know. So this is the quote-unquote algorithm for doing a right rotation. Now, you might ask yourself, why am I using letters and numbers here? Well, I'm doing that because I'm trying to indicate the location of where the children go whenever you have these rotations, because we always have to think about the children, okay? So imagine that you have a situation of x, y, and z, and that is what we saw right there. Let's say we have a 1, 2, and 3. X is equal to 1, y is equal to 2, z is equal to 3, okay? So we have something that is unbalanced clearly. It just got unbalanced because we maybe inserted that 1. So it is possible, even though we just inserted it, but in other scenarios where we might have brought unbalance where there wasn't before, that x has children on the left and the right. It's also possible that y has a children on the right, as we just saw by your question. And finally, that z has children of its own as well on the right, which we also saw in that previous question that you said. So in this case, whenever that happens and you perform a right rotation, the children will always end up in these spots. It's good because that makes coding a lot easier. You just basically hard code these locations. So as you can see, the 1 and the 2, in fact, it's always going to be 3 of the 4 children will not be moved. There's only 1 child that will always be orphaned and readopted. So only one of the pointers is going to change. The other 3 will not change. Okay? Which one changes depends on which rotation it is. With this right rotation, which is what it's called, the 1 and the 2, which are the children of the X, if it had any children, because probably it's the one that you just inserted, they stay in the same spot. They don't get changed. So if you just inserted it, they should have no children. If for some reason this became unbalanced and it had children already, then those children will remain as they are. You don't have to worry about it. As long as you move X and the pointers are set up correctly, the children will move along wherever mom gets relocated to, essentially, okay? Z, on the other hand, will keep its right children to the right. So as we saw, the 4 kept the 5 in the same spot as it was before. However, Z is the one that's going to aggressively adopt the previous children of Y that was on the right. So as you can see, I highlighted that in blue to indicate the 1 children that gets changed. It becomes from the child of Y and gets adopted by, I suppose, the granddad. So it's kind of like the dad gave the kid to the granddad to stay over for the weekend or something. I don't know. Okay? So yeah, that is changed. Now, what is the difference between that and the left rotation? It's just the mirror of that, essentially. So you have the other situation where you have something like 1, 2, 3, but in this order where X is equal to 1, Y is equal to 2, and Z is equal to 3. In this case, the rotation is going to be that the Y is going to be the one that's going to be pulled up. So in this situation, again, 3 of the 4 children do not change spots. The children on Z, which is probably what you just inserted and made it unbalanced, probably doesn't have children anyways. But again, if it did, those children stay in the same spot. The left child of X doesn't change either. And then the only one that changes is again in the middle, that Y. Is going to become the new root, and so it needs to pass off his children, in this case, to the old root. So the new root gives the child to the old root, okay? New root gives the child to the old root. Just make sure he gives the right child. And by right, I mean the correct child, not the actual right child, because the right child technically would work in the right rotation, but here's the left child, okay? So, yes. 1 child moves, no other child. Do not orphan children for no reason. Only one of them is allowed, okay? Per rotation. So that's the left and the right rotation. Like I said, if you know one, you know the other, because it's literally just the opposite. Like look at a mirror and then you got it. Okay? If I zoom out, you can see that they're both pretty much the same exact thing. Now we still got to do double rotations, but let me bring you to a scenario where that is required. Okay? So let me let's just insert stuff until we end up with a double rotation. That'll work. Oh, now never mind. I got one that's easy. Perfect. Okay. So just to make sure we're on the same page, let me do one more example of inserting. In this case, or have we done one already? No, we haven't done one. So let's do one with the left rotation. By the way, why are they called left and right? Because like to me, it feels backwards because again I'm left-handed maybe. But the reason being is because you are rotating in the direction that you want to restore balance. So like, for example, this tree right here is right heavy, right? Because the right side is very heavy. Like the X is hanging on to its life on the right because it's super heavy. And on the left side, it's like nothing. It's got 1 child maybe, if even, okay? So it's right heavy. So you gotta rotate it to the left to make the right not so heavy, right? So the rotation is kind of happening this way, okay? So that's why it's called the left rotation. This one, on the other hand, is left heavy. The left is really, really heavy. You know, the Y and the X are putting a lot of burden on the Z, right? And because of that, we want to move some of that weight to the right side because that has no weight right now. So as we move that weight over here to achieve balance, we are doing right rotation. So that's why the names seem a little bit backwards because they are implying which way we are rotating to restore balance. Oh, we got lots of people doing the extra credit. See? So we get like 4 people in one day. That's how it used to be in the summer, but it would be like every other day. with the lowest amount of points, which was a pain. That's why I made it such a high point system, because then it's like once every like month and a half you guys do the claim, so it's nice. Okay, so I like that. But anyways, for those of you, make sure you send me a message on Discord with your name so that I can award the point to the right person. Okay, so that's left and right rotations. Now let me give you a example of that right rotation, I suppose. Yeah, no, left rotation, whatever. So we're gonna do 1, 2, 3. Yeah, so 1, 2, 3. The 3 is the one that breaks the balance. So then we go ahead and we do that. So there you go, bam. Example of the other rotation, again, we already did, but just to make sure we're again on the same page. 3, 2, 1. In this case, it becomes 2, 1, 3, right? So in this case, we kind of rotated it to the other way. So I guess that's a right rotation, and this one's a left rotation. So left, right. I don't care, by the way, if you call them left or right backwards. I care about seeing the rotations, the correct rotation being used. So I don't care if you're naming them wrong. You don't even have to name them. What I want to see in the test is this thing here: the old tree, the arrow, the new tree, so I can see the before and after. That's how I know you know your rotations. I don't care what they're called. I want to see that. So in the test, you're going to be Bob Ross drawing all these trees by the end of it. So, yes. Okay. I suspect that they're watching the 202 lectures. That's probably why. But yeah. Okay. That's fine with me. So anyways, let us go ahead and talk about a special case. What was that? So let's see. We're going to put a 3, a 1, and a 2. Yeah, there we go. 3, 1, 2. So simple, yet so evil. We're going to put the 3 in. From there, we're going to put the 1 in. The 1 is less than the 3, so it goes on the left side. Okay. Let's check heights. 0, 0, 1, 0. Everything is good. Cool. All right, let's put in the 2. 3 is less than 1. Sorry, 2 is less than 3, so it goes on the left. But 1 is greater than 2, so it goes on the right. So this is the tree you come up with. Okay, so you recompute your heights in your algorithm, and you find that balance has been broken. Okay? So, according to what I've taught you so far, this is telling me that this tree is left heavy. Therefore, I must do a right rotation, right? So what is the right rotation? Let me copy and paste it here in really small font so that you guys can have it for reference. This is a right rotation right here, right? It's the one that you know, it kind of goes from being sorry, the mirror this way to this. So this is the thing, okay? Okay, so according to this algorithm, the y should be, so let's label these. So basically this is my z, this is my y, and I don't really have an x, so I'll just put like an imaginary x here so that I can kind of follow the algorithm. This is a very useful thing to do. And then do the same with the children. So there isn't really a child here nor a child here, so the 1 and the 2 from this up here, you know, we don't have those, but we do have a 3, which is actually the 2 here, and then we don't have a 4. Okay, so based on this algorithm, the y, which is the 1, should be the root, and then the x, which we don't really have, would go here, so there's nothing there. The z, on the other hand, is going to be the 3, right? So we don't really have anything there. And then we got to move the children. So 1 and 2, there's no children. 3, which would be the child, would get readopted by the 3, so that means it would technically go here. And then 3 had no left child, sorry, no right child, so that's it. So we end up with this 3 essentially. So we get rid of this temporary stuff again, just so you can see it. And we end up with that. Okay? So when we finish rotating something, we always want to verify that it worked or it didn't by checking the height. So we start checking the height again. And then we find that we still have a problem. The problem was not fixed. In fact, we kind of like mirror the tree in a way. Not quite mirror the way that the assignment is, but like you can see how it looks kind of like we just flipped it around. So you're like, well, now it's right heavy. So therefore we got to do like a left rotation, right? So, you know, when something doesn't work, when your code doesn't compile, who knows? Try to compile it again. Maybe magically it compiles now, right? So we try doing the rotation again. Okay, in this case, we're going to try the left rotation. So let me go ahead and copy that algorithm again here. At this point, if you were taking the test, that's when you start sweating and you're like, oh no, something bad is going on, right? So yeah, you're like, okay. So in this algorithm, x is equal to 1, y is equal to 3, and then z is equal to 2. Oh, no, z is nothing. There's no z, which means that there's no 3 and 4, which is fine. And 2 is equal to 2, and then there's no 1 here, okay? So we do the rotation, which means that the 3 becomes the root, the 1 becomes the left child. There is no right child because there was no there was no z, which means that nothing is here. And then the 2 gets readopted by the 1, which means that it goes here. Okay, so that's what we end up with, which is literally what we started with. So we just kind of went in a circle back to the beginning. And of course, now it's left heavy, therefore we do our right rotation. So we go here doing this all day until we, you know, sec fault if we're running it in code, right? So as you can see, we're stuck. We are essentially stuck. So what do we do now? Well, one option is to just panic. Other option is not to panic. So we're going to choose the option not to panic. We are going to do a double rotation. So let's say we don't know what that is, which we don't. Well, let's analyze the problem and kind of derive our own sort of fix for this. The problem is that our rotations are not working because the thing is not in a straight line. You know, the left and right rotation works so great because we have something of this format, which very naturally works because, you know, this thing just kind of the top sort of just falls down, right? It goes from this into like this. So can we just convert what we have right now into something that is a straight line? Because if we can do that, then we can just call the single rotation, which we know will work. Okay, so yes, that is a solution. All right. So instead of trying to do the rotations on this guy, let's look at the child and grandchild. So let's look at this. This is the real problem because this is right now in this format when we want it to be in this format. So what do we do to fix that? Well, let's just make it into that format, which means go ahead and reroute that child with the grandchild. So essentially rotate or do a rotation on these nodes. So essentially rotate them to make the 2 and the 1 like that. Because if we can achieve a rotation and make it into a straight line, then that's okay. We know that that will for sure work out and make it into a 2, 1, 3, right? But the question is, how do we do this algorithmically? Well, we can actually use the rotations that we've already implemented in code. Okay, how do we do that? Add an imaginary node here. Let's call this imaginary node question mark. Okay? If we add that imaginary node there and we recompute our height, we can see that now it's unbalanced at this level. And now it's in that beautiful straight line that we can now perform a rotation on. So what happens if we perform a rotation on that? Let's try it out. So we have this, and we're just adding our imaginary node. I'm going to kind of actually node blob. Yeah. I was going to say, I was going to use X, Y, or Z, but I don't want to confuse you with that stuff earlier. So if we do that, we can perform our typical rotations. In this case, it would be a left rotation, right? So Let me copy and paste that algorithm again. So how do you know, first of all, that you have to do this? Because you try doing the simple way and it doesn't work. You do it again and you come up with the original one. That's your sign that like it's not going to work. Just give up at that point. You did it twice. It's not going to work. So because you're going in a circle at this point. So at this point you see this and you're like, okay, I got 1, 2 in this. So I put in the temporary node and then I can follow the same algorithm as before. Obviously I got to fill in what each thing is. So in this case, I see that X is equal to 1. Then Y is equal to 2, and then Z is equal to the blob. That's okay. What about children? Well, convenient, there's no children. No children here, no children here, no children there. If there were children, that's okay. We could name them children's like 1, 2, 3, and 4, and then move them in the right spot. But anyways, once we do that, then we perform the rotation, which is to make the Y be the root, which in this case is a 2. And then the X, which is the one, goes to the left. As you can see, this is what we wanted to go for. And then our blob gets moved over here. And then the children, which there are none, but if there were, they would go, the left child would stay the same like that, which there isn't any. And then the blob's childs, which are 3 and 4, would stay in the same spot, which there isn't any. The only child that would move would be the child that would be to the left of the 2, which there isn't any. But if there was, it would get moved there, okay? So lots of fancy work for pretty much just something rather trivial, because once we remove the blob, which is just a fake node that we added, and the fake children that we added, all we did is just rotate basically from that to that. But that's exactly what we need, right? Because this thing is connected to something. What is it connected to? It's connected to the tree, right? Because this is a subtree. So yes, we made this subtree's root to be the 2, but this is still connected on top to the 3, right? But that's great because, again, we went from this to that, which is exactly what we need. Because now that we have it like that, we recompute our weights. We see that it's unbalanced. But now, as you can see, when we perform the right rotation, it's going to be balanced. So that solves that weird scenario that we just had. So this is what is known as a double rotation because, as you can see, it's technically 2 single rotations. The trick is that the first rotation is not done on the node that's unbalanced. It's done on the child of the node that's unbalanced. So if it's unbalanced left heavy, so if you have a node and you got a big number here that makes it unbalanced and you try to perform a single rotation and fail, then you perform it again and you come back to the original, which it'll always bring you back to the original, by the way. These rotations, do them twice, you come back to the original. But if you do that and you end up with this, the next thing you do is don't try to do rotations on this guy. Do the rotations on the child. So do them on this. That's what you want to do the rotations on that. And then if you do that, and how do you do that? Just add that temporary node to make it easy to do the rotation. And when you do that, you basically fix the problem. You fix it from being like this into basically being the straight line, which is exactly what you want, so that this thing fixes. Because then you can now perform this rotation, which will bring this as the root, and you will end up with that, which is of course what you want, right? If we label this as A, B, and C, this is A, B, and C. Okay? So now that I've shown you that conceptual way, let's look at the algorithmic way, I suppose. So the one that we just did is actually the we actually did a left-right rotation technically, okay? So the only nodes that we have here are the Z, the Y, and the X. They, of course, can have children of their own, but in this scenario, it doesn't matter. We have, again, there's only one child that gets moved around with every rotation. Only one child, never more. But in this case, because we're doing a double rotation, technically speaking, each of those could move a single child. So how did that get moved? Well, we started with Z, Y, X, and as you can see, we are using the 3, that child, even if it doesn't exist, we are adding it in temporarily so that we can perform that left individual rotation. So that basically changes this structure into this structure, which is perfect because this, this is the Pac-Man mouth is bad. The straight line, that's what we want, okay? So essentially this with a single rotation becomes this, You see that? yx3 becomes yx3 like that. See, it's just a single rotation. The children of the y, you know, the 1 is in the same spot, and then the 3 is in the same spot, and then the 4 up here technically is in the same spot, but that doesn't get messed around actually here. In this case, technically speaking, this might have 2 children, which again would not get moved around. They just stay here. This is what gets moved. It gets, oh, sorry, no, sorry. The 2 gets moved. The 2 gets moved from here to the y. Okay, so there's the same movement that we did before. And then once we achieve this, then it's just a single rotation again to achieve this. Okay, so again, all you got to do is rotate the child and grandchild from this sort of Pac-Man shape into a straight line. And once you achieve that, then just do another single rotation, this time on the proper node that's unbalanced, and you will achieve balance. Okay? And then, of course, the right of the rotation is the same thing, just backwards. So you have something like this. So the problem is, if you try to rotate this twice, you will see that this goes from this, actually, to this. And then back to this. And you're like, ah. So in your code, you run it once, it's not balanced. You can either at that point call this rotation on top or just run it again to come back to the original one, which is what I recommend. And then go ahead and call your double rotation function. So your double rotation function will look at these 3 nodes, and instead of trying to perform rotations on the node that's unbalanced, it'll do it on the child of the unbalanced side, which is in this case the right side, or in the other case would be the left side. Okay? So you perform that rotation there. More than likely you probably don't have a node here, but if you do, that's okay. Just do that rotation there, and you will end up with this shape here. When you do this, now you will still see that it's unbalanced up here, but that's okay because you're doing a double rotation. Now you would just rotate again on this node now, back to the original node, and then again, you would achieve balance. Okay? So, yes, questions on that? I like unfinished water bottles. I have a little bit on it. So for the last few minutes, we're just gonna do some insertions and kind of just go with it, and then maybe next class we'll do more practice, and then move on to heaps. But AVL trees, as you see, is tricky, just because you gotta make sure that you don't make mistakes along the way with the rotations. You keep track of the children. As you can see, I've kind of put the algorithm side by side. You don't have to do that. I'm just trying to show you that it's a good way to keep track of things, but you can also kind of just, after you do it a while, just do it without it, get practice with it like anything else. And here's the thing. Tests have a limited time to do them. So it's not enough to just kind of know something. You have to be fast at it. You have to have practice so that you can do it second nature. That's how you don't run out of time in tests. A lot of people they're like, well, I kind of know what's happening, and if not, I kind of work it slowly. That doesn't work with a test. With a test, you have a limited amount of time, so it's not enough to just know a concept, but you have to be able to reason it quickly and not have to be stuck trying to reference things. So while yes, I do recommend that you definitely have these rotations available on the test, printed out or something, side monitor or whatever. It's not enough to just kind of hope for the best. You want to get practice and be fast with this stuff, okay? That is why people sometimes complain they run out of time, because they know something, but they don't know it good enough to do it rather quickly. It's like, I'm not saying you want to solve the Rubik's Cube in 10 seconds. I'm just saying you want to be able to solve the Rubik's Cube in a minute or two, and not just be like, well, I have the tutorial on how to solve it depending on the configuration, but it's going to take me time to go step by step. That's not good if what you're trying to do is do a test. So anyways, do I have an example here that comes up with cool rotations? Oh, wow. That's an interesting example. I forgot I did that as an example. We actually used the word poliovirus. I suppose that actually worked out really well, but those were different times, less sensitive times, I suppose. So we don't want to do that as an example. Kind of weird taste. Let's just go ahead and do. Oh, by the way, starting with AVL Trees for sure, there's video lectures available from last semester. So if you want to watch more examples on AVL trees and rotations, I welcome you to watch the lecture from last semester on my YouTube channel. That way you can get more examples. I guess you'll see that poliovirus example, which actually worked out really well for insertions. So interesting. Okay, for us, we are going to do. Anybody have let's whatever. I'll just pick one. We'll do Anakin, okay? Since he's supposed to bring balance to our tree. Okay, so and we can keep inserting things as we go. So all right, let's just kind of go quickly. So A, that's okay. We're not gonna check balance when it's obviously balanced here. And we're gonna go with alphabetical order, increasing. So A is gonna go here. It's still balanced. The K, where does the K go? It's greater than the A, but less than the K, right? Yeah. Where's the I? Okay, so I think the I goes here. All right, now I can see things getting iffy, so we'll check the balance here. And yeah, that is right. We have a problem. We have a problem right here. We don't keep going further. We fix the problem immediately with the AVL tree. So after insertion, you want to check your heights and fix them out immediately. Don't just like insert everything into the tree and then start balancing it. That's not the algorithm. The algorithm is you balance as you go. Okay? So this is simple. It's going to be, I mean, even if we don't know if it's a single or a double rotation. I mean, we know now because we see it, but we might not know if it's in code. So you just assume the easy case, right? Should there be two ends? We haven't gotten there yet. We've just inserted the I. That's what I'm saying. As we insert, we check for balance. Right now, we just inserted the I. We still have to insert the N, but we don't insert it yet. We balance the tree before. That's what I'm saying. Like, you don't just insert and then balance after you finish inserting. That's how kind of like heaps work in that manner, that you first throw everything in and then you heapify. Trees, AVL trees don't work like that. Trees are, you balance on the go. So you always keep it balanced. Otherwise, things get messed up and it takes longer to balance trees. If you balance them as you go, then you save yourself like massive headaches, basically. So yeah. Anyways, so in this case, it's left heavy, so we do a right rotation. So, you know, basically it becomes that. I has no children, but if it did, they would not change spots. And then N has no right child, so doesn't need to be, it's, again, would say the same. Even if it did, it would stay in the same spot. The one that would be moved there was if K had a right child. If K had a right child there, then it would be adopted by N as a left child, okay? So basically it replaces its child with its grandchild. Should be like a Star Wars thing too, probably. But okay. Anyways, yeah, like Darth Sidious replacing Darth Vader with Rey. Well, that's kind of like the great grandchild technically, but close enough. Okay. So yeah. All right. So anyways, that has achieved balance. So let's go ahead and draw our new tree. So we get the K, the I, and the N. And so now we can go ahead and insert the last N, because now we check the tree to make sure that it's balanced, which it is, you know, 1, 2 there. That's okay. And so now we can go ahead and insert the last letter, so the N. So where's the N going to go? It's going to go to the left of this N. That's probably going to break balance, but I'm not sure, actually. No, yeah, I think it will. So this is good, actually. I think this one's a double. So this becomes a 1, and then this becomes a 3. Ooh, yeah, I like this one. So here we have unbalance up here, right? I don't know yet, but I do think it might require a double rotation. We'll find out. So in this case, the unbalance is here. So we are going to try and rotate this. Okay, that is basically our, and for this one, I will copy the algo. Okay, so that's basically that. So x is equal to, x is A, K is Y, and Z is N. And so from there, you know, K becomes the root, A is the left child, N is the right child. But now this one's have children, so we can actually follow along. So first of all, we see this one right here. The left child, A, should remain in the same spot when we do the rotation. So A remains there. And by the way, one way to double check that you didn't screw up rotations is to look to see that it's still a binary search tree. If you do this rotation and like you get like an N over here, that violates the fact that it's not binary search anymore. That's a big sign that you screwed up. So that's when you be like, whoa, 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 whoa. And then you're like, oh, I see my mistake, okay? So that's one good thing about this thing. You can definitely use that to your advantage in the test. Okay, or actually even when you're coding it too, but primarily for a test. Anyways, that's where children 1 goes. Let's do the other 2 easy ones, which are the children of K. Children of K are these guys. As you can see, they don't basically get moved. So in this case, it had a child of I and a child. Oh, wait. No, sorry. I almost screwed up. Z in this case is not K. Z in this case is N. So actually, we're looking at these children. So these children are the ones that we're looking at here. Okay. So in that case, this doesn't move, but then this one had no child in the first place. And then finally, we have the child of K, which gets moved from here to here, which means from here to here. So it gets adopted by the Y, by the A, sorry. Okay? All right, so I guess we didn't need a double rotation. That's good because we are out of time, so that actually worked out. I hope we didn't eat a letter. Do we still have our letters here? Anakin, Anakin. Yeah, we do. Okay. And we have achieved balance as well. So we're okay. So I guess that only was a single rotation. It looked like it needed a double rotation, but it did not. So that's fine. Maybe we'll add more to this next time. Okay? So that's pretty much AVL trees. I hope very much that my explanation of them was clear, and the fact that we trying to derive the rotations instead of just me giving it to them and being like, those are the rotations, good luck, have fun, implement, because that makes you understand them better as to why they exist. And I am of the strong belief that it's better to understand something than to memorize it, because A, you'll remember it for longer, but B, if you run into mistakes, because you understand it, it's a lot easier for you to fix them when it comes to programming. You will have to do this, and you will do the AVL version of the first assignment. So you've done linked list, you've done vectors, I think. Now you will do the AVLs of the Sith fleet. And the last order will, what is the quote? The work of generations is complete. The great error is corrected. The day of victory is at hand. The day of revenge. The day of the Sith. Yeah, there we go. So yeah, any questions? Would you agree or disagree that it's the hardest topic? Maybe you found this easy, and if you didn't, that's really good, because that means that nothing else in this course will be tricky. It's like peak difficulty of coding as well. I think maybe the coding part is the people that gives them headaches, coding this stuff. But as long as you're very consistent and you code those rotations the way they should be, then fingers crossed, the code compiles, and more importantly, it doesn't segfault. Because compiling is not the hard part with AVL trees. It's the fact that you don't want to accidentally segfault because you're losing nodes or creating memory leaks and other scary stuff that can happen. So anyways, I don't see anybody saying anything, so I'm going to assume that you guys are good to go. So, all right then. Well, thanks for watching. I hope this is good. Even though the AVL, you can do the AVL tree assignment now, I'm going to post it up, but it's going to be due for a while because you got to first finish the other assignments. So focus on those now, but definitely keep AVLs in the back of your head or your mind. And yeah, I'll see you guys later. Thank you all for being here. I'm glad to have you guys here. And take care, and see you guys next week. Bye.